So if we've got a mass spectrum for an element, then it's actually relatively easy to interpret, because when we look at the mass spectrum, each of the peaks that we see here is for a particular isotope. So I can see straight away from looking at the mass spectrum of zirconium here that it's got 1, 2, 3, 4, 5 isotopes. Is everybody okay with that? Yeah? And the height of the peak tells you how abundant that isotope is. So can you see that this one is the most abundant because it's the tallest of the peaks, and that this one over here is the least abundant because it's the shortest of the peaks. Does that make sense? So basically that's all we get. If we put an element in, then we'll be able to see the number of isotopes, the masses of those isotopes, and the abundance of those isotopes. Okay? But what we actually get on this axis is not purely the mass, it's the mass divided by the charge. Where M is mass and Z is charge. And because most of the particles that you put into the mass spectrum get one electron knocked out or one proton added, then most of the time that charge is +1. And if I divide a number by 1, I just get the same number. So usually at the bottom there, that is going to be equivalent to the mass. Yeah? Because usually I'm just dividing the mass by 1, so mass over charge is usually equal to mass, but not always, and it's worth bearing that in mind. It can be +2. In theory, it could also be +3, but it's very unlikely that you would have managed to knock out 3 electrons during electron impact, because all of the atomic samples, all of the elemental samples, would be ionized by electron impact. Has anybody got any questions about that bit? Does that make sense? Okay. So when you do exam questions, in the past, they would tell you the percent abundance and the mass of the isotope. Yeah, you'd get it in a table. So now what they could do instead is give you one of these mass spectra, and you would have to read off the mass of the isotope, and then you'd either have to use the scale or measure to find the relative abundance. Okay? So we can also, instead of finding it for elements, we can also find the mass of a compound. And this is slightly different. And I can't remember if we talked about this at all. This one's a little bit harder, so we probably avoided it. So the molecules that are ionized by electron impact, the signal with the greatest MZ value, so what I mean by that is the largest numerical value. We did talk about this actually, didn't we? Yeah, but I think some people might have got a little bit confused. I know the other class did. So this is from the molecular ion, and its MZ value gives you the relative molecular mass. So what we said last time is that you have to only look at this far right. Yeah, these are the largest numerical MZ values. So when you say the greatest MZ and the largest MZ, it doesn't mean the tallest peak, it means the one to the furthest right. Okay? So we have to look all the way to the furthest right on the axis, and we sometimes see a very small peak. That is one mass unit higher than another peak next to it. This peak here is due to heavy isotopes of hydrogen and carbon. So we would look at this, try and find the mass of our molecule. We look to the furthest right, And we can see we've got two peaks, but one of them's very, very, very small. If the very small peak is just one mass unit higher than a peak next to it, then it's just due to the presence of heavy isotopes. Usually you would only get one of these heavy isotopes because they're rare. They're common enough that we do get them, but they're not so common that the chances of having two in them are high enough for us to detect on here. So occasionally we might get something with two in, but it would be so rare that we couldn't see the little peak on our graph. And so this is actually the normal MZ mass mixture of this particular substance. And it tells us here that this particular substance was propane. So we can check what we would expect the mass of this to be, which would be 15 plus 14 plus 15, which is 44. I know it might seem strange that I did 15 plus 14 plus 15, but I know that CH3 groups have a mass of 15 because I have to add them all the time, and so a CH2 group must have a mass of 1 less than that. You would probably have done 12 plus 12 plus 12, 3 times 12 plus 8 times 1. But to me, that's much slower because I'm not very good at my 12 times table, whereas I can add those a bit faster. It doesn't matter though. So it would be unusual for us to take something we knew what it was and put it in a mass spec. Why would I take it knowing that it had a mass of 44 and try and find out its mass? That would be a bit odd. But we can actually show that that is where we expected to find the peak. We do not have to worry about any of the ones over here. I was hoping to change the colour. That was not very successful. So all of these ones we ignore. Okay? These ones are called fragments, and fragments are not on your specification. If you find yourself in an exam starting to write the word fragment, stop. This is not the answer. Now, despite me having said that very clearly to the other class, when they did the exam questions on the next page, some of them wrote the word fragments. Right? That is not the answer. You're going to be better than them. You're not going to write the word fragments. The answer is something else. Just they panic when they don't know the answer. It must be fragments. Fragments is not on your specification, so it can't be fragments. But these fragments, perhaps you could imagine that when you're firing high-speed electrons from an electron gun, you might accidentally break a bond. And can you see that that would give us a fragment with a mass of this little bit here? Yeah, and depending on which of the bonds I break, I can get different pieces, and I can then detect those. But you do not need to worry about that. Yeah.
I'm a bit confused. What is, you know, the big one at the end?
This one?
Yeah.
That one?
What is it?
So that is the mass, that is this whole molecule with one electron knocked out.
So the mass of it.
And so, yeah, that is the molecular ion. And so remember that on this axis, we're going to see the MZ, the mass over the charge. And the heaviest thing we could possibly get would be the whole thing with one electron knocked out. We can't get anything heavier than that. We can get things that are lighter than that if we break it apart, but we can't get anything heavier than that. So this peak here is caused by the molecular ion, which is the whole molecule with one electron knocked out. Does that make sense?
Because aren't we trying to find isotopes?
No. There we were trying to find isotopes. Here we're looking at molecules. So there's two different things we can do in mass spec. One of them is we can look at elements, and that will enable us to find the isotopes. We can find the masses, and we can find the abundance. But that is up there. The second thing we can do is we can look at molecules, so more than one atom joined together. When we do that, we end up with these more complicated looking spectra. But do you remember there's two ways we might ionize a molecule? If a molecule is small, then we'd use electron impact. And that's where we get a spectrum that looks like this. Because we're sheeting it, we can break it, and we get this complicated looking spectrum. This is quite a small molecule. It's not got that many atoms in it. And yet look at how complicated its spectrum looks. Imagine if I took a protein that had hundreds of atoms in it, how complicated this would look. And so if molecules are big, instead of bombarding them with high-speed electrons from an electron gun, we actually use electrospray ionization, which is where we add a proton to the samples to ionize it. We give it a proton as it comes out of the hypodermic needle attached to the high voltage terminal. Remember that bit? Yeah? So this particular example here is looking at electron impact because my molecule is relatively small. There is no cutoff that you have to learn that tells you whether you'd use this one or this one. In a question, they'll make it pretty obvious. They'll either give you something that's big, or they'll give you something that's small, or they might ask you to suggest which type, or deduce which type of ionization you might use, okay? But in the spec it says like things like proteins, so we're talking massive things. Here, this is your regular kind of things that you might be able to actually draw yourself, yeah? So if you've been drawing like hexane in the past, that's okay, yeah? Things that you might have to draw this way, things you would never have to draw this way. Does that make sense? So when you're looking at the spectra for this one and this one, they will look quite different. So this one, the electron impact kind, has lots and lots and lots of peaks. Many of them quite tall. And many of the tallest ones are not the whole molecule at all. Some bonds are just more likely to be broken than others. Just like if you think about me trying to shoot you, there are certain bits of you I'd be more likely to shoot off. You can imagine how I might get a pile of arms and a pile of legs, but it would be quite unusual for me to get a pile of little toes. It could happen, but the chances of me managing to shoot that bit off would be a lot less likely than me managing to get it here. Yeah? Quite likely, especially because I'm quite a good shot. Useless at all other sport, but I reckon if I had to be in the Olympics, maybe shooting. That's so right, that's so belittling all the people that are actually good at shooting. So I've only done it like 6 times, but I felt quite good at the time. So we use this one to find the mass of whole molecules, yeah? And we ignore all the peaks except for the ones at the very far right, which have the highest numerical MZ values. Usually, it would be the highest one that would be most interesting to us. That would usually equal the MZ, the MR even. Whereas this little tiny one next to it, if you've got a tiny one that's 1 mass unit higher, it's caused by the presence of a heavy isotope of either hydrogen or carbon. Is that one okay? Anybody got any other questions about that one? So, I think I might have sketched this next one for you as well, but I know it's quite hard when you're not looking at it with me. You can't ask questions. So the other kind of graph you can get is by electrospray. It says in the next example, and it talks about peaks, but the graph is missing. So I'm going to sketch it. I think I got you to do this already, but I'm not sure. Was this the very last bit we did? In a bit of a rush. So on this one, you'd expect to see a peak here and a peak here. And this one here is at 521.1. And this one, there's a typo on here, is at 522.1. Okay, so can you see the graph is much simpler? It hasn't got very many peaks on it at all. There are no peaks with low MZ values because I'm not shooting it and breaking it into pieces. I'm adding a proton to it. And that means that I don't get it broken up and I don't get all those lower peaks. So it's a much simpler looking spectrum. I have still got a peak here that's caused by heavy isotopes. My 2H and my 13C. But actually it's quite easy to find the mass of the whole molecule. But this is the one that I got wrong when it was in the exam, because I forgot that here, when we do this type of ionisation, we've got the molecule with an extra H+, because that's how we ionise it. We ionise it by giving it a proton, and so actually the mass is therefore the whole thing there minus 1. And it's very easy to forget to take that 1 off, especially because I think there's only been 2 exam questions that have asked you to do this that we've got. So you won't have very much practice of it. So I think that makes it easier to forget. So with these, if you've got electrospray ionisation, you'll get a very simple looking spectrum, which will not have very many peaks at all, probably only 2. One of those peaks would be caused by the presence of heavy isotopes, and it would be very, very small. And the other peak would tell you the mass of the whole molecule with 1 extra proton. So to find the mass of the molecule, you have to take 1 away. Does that bit make sense? Anybody got any questions about those? Okay. So the mass spectrometer can be used to find the relative molecular mass of covalent molecules. The greatest or highest, but being careful to realise that I mean the highest number on the x-axis. I don't mean the tallest peak. The highest number on the x-axis, the greatest numerical NZ value, will be the MR, the molecular mass of the whole molecule. But remember, if I've used electrospray, I do have to take 1 away. Okay. So isotopes in molecules can also occur. So it's quite straightforward when I've got an element, just atoms of an element, because when I've got atoms of an element, I can just see the isotope straight off. So if I put carbon into a mass spec, then I'd expect to see a peak at 12, and maybe a peak at 13, maybe a teeny peak at 14. I can just see the isotopes straight away. Yeah, that's if I've got atoms of an element. But if I've got things inside a molecule, it can be a little bit more complicated. So there are two atoms that we have to be particularly cautious about and remember to look for. So as the mass of individual ions is measured, ions that are otherwise the same but contain different isotopes of the same element will appear at different MZ values. This is most noticeable with bromine and chlorine, as they contain significant amounts of different isotopes. They only produce tiny peaks for other elements, so you wouldn't really notice them in a mass spectrum for other elements, but you're going to really notice them for bromine and chlorine. So bromine consists of roughly 50% of one isotope, bromine 81, and 50% of another isotope, bromine 79. Chlorine consists of 25% 37 and 75% 35. So if a compound contains 2 or more chlorine or bromines, the spectrum becomes more complicated. So if I look at a relatively simple thing, oops, like that, that's methane, yeah? I'm going to change mine. If I turn it into chloromethane, I can have CH3 and 35Cl, and CH3 and CH3 and 37Cl. Yeah? And actually I'm going to have quite a lot of both of those, because both of them are reasonably abundant isotopes. So if I take a sample of chloromethane, I would expect to see 2 peaks. One of them here, one of them Which one's the lighter one? Which one's the lighter one? This one, heavy. No, there we go. I would expect these to be on a 3-to-1 ratio. Yeah, and they would both be molecular ion peaks. One of them is for that, and one of them is for that. Does that idea make sense? If I look at the same thing with bromine in it, bromine's isotopes, instead of having a 3-to-1 ratio of them, they actually are equally abundant. So I'd see 2 molecular ion peaks of the same height. One of them would be CH3 79 Br, and one of them would be CH3 81 Br. But that's when I've only got one atom of bromine or one atom of chlorine. If I had CH2 Cl2, I could now have 2 35s, 2 37s, or one of each. So I'm going to get 3 peaks. I can also get those the other way around, but they're going to have the same mass, and so they'll appear as the same peak. But I've now got four potential ways of arranging my atoms, and so I'm going to get more complicated peaks. And I need to bear that in mind when I'm analysing spectra that contain chlorine or that contain bromine. And they really like asking questions about chlorine and bromine. Most people remember that chlorine has 2 isotopes because you do it quite a lot, and it's straight away obvious from the periodic table because of the mass of 35.5. Problem with bromine is because it's got 2 equally abundant peaks that are 2 mass units apart, when you average them, you just get 80. So on the periodic table, you can't actually tell that it's got these 2 isotopes. And so you need to learn that bromine has 2 isotopes, 79 and 81, which you can work out just by going one less and one higher than the mass on the periodic table. But you need to also know that those are equally abundant, and that can lead to interesting peaks on mass spectra. Because even if I've got a completely pure sample that hasn't fragmented at all, I would still get a peak, 2 peaks on for my molecular ions. So if a compound contains 2 or more chlorine or bromine atoms, the spectrum gets more complicated because I can have 3 molecular ion peaks caused by the, remember, all of these pluses when I'm actually detecting them. And I can then also get little peaks 1 mass unit higher due to the presence of these other isotopes. So they can be quite complicated looking. These will be a little bit more obvious when you actually try some questions on them. And in this week's homework, there's a couple that are a bit challenging that I've set it on Google Classroom to go live at 10, I think, so that you can start looking at it beforehand. Okay? So here's just some examples of some mass spectra of compounds. So when I look at the mass spectrum of a compound, where do I have to look? What bit am I actually interested in? I have to look to the furthest right, the highest numerical MZ value. And that will tell you the mass of the molecule, or the or the relative formula mass. Okay. Hi.
Will you turn the computer about? I can't see
Oh
the
yeah,
screen.
sorry, I knocked it. There you go. I forgot that I couldn't use that. It's weird seeing a computer there that I shouldn't touch. Okay, so I totally ignore the other ones. They don't matter to me at all because do we have to worry about fragments? No. Okay, so this here is what I'm actually detecting. That is my molecular ion. You can see on here, these have got a dot as well as a plus. That's because they now have an unpaired electron. These things are called radical cations, which makes them sound like they're going to try and change the world. You don't have to worry now about showing that they're a radical cation. If you did it, it's correct, because they do have an unpaired electron, so they count as something called a free radical, that you'll study a bit later on. If you just wrote it like this, or even like that, these would be fine, okay? But because on the old specification, when you did do fragmentation, you had to be able to write fragmentation equations, you had to write them like that. So when you see the dot, that's what, it's not just an accident, it was there for a reason, but you don't need to worry about drawing it anymore. So on this one, for methyl acetylate, what's its MR going to be? Yeah, to the far right. Okay, so don't worry about any of the others. So as soon as you know what to do, these are actually relatively easy, especially if they've not put that little 1 mass unit higher peak. So what you can sometimes do, you know, if you're watching like a crime thing and they've been recording conversations, you can sort of blur out the background noise to make the bit you want to hear a little bit clearer. They can kind of do that with these spectra. They can blur out the little tiny peaks so that they're not really there anymore to make it look a bit smoother and clearer. So if you get rid of everything under a certain value, it can be a little bit easier to read. And so these ones, they kind of just blanked out those peaks. So sometimes you'll see ones that are higher resolution and show that little 1 mass unit higher peak, and sometimes you'll see some that don't. Okay? But what's important is that for all of these, you just look to the furthest right. Okay? So can you see we've got examples now of things that contain bromine and chlorine. So they're slightly more complicated. So if you get 2 peaks that are both quite abundant and are 2 mass units apart, then this is an indicator that bromine is in your sample. So if you didn't know before, this is helping to tell you, to give you a hint that this contains bromine, because bromine has those 2 isotopes, 79 and 81. So we end up with 2 molecular ion peaks. They should both be almost the same height because they're 50-50 likelihood of occurring. Chlorine has a similar impact because here, again, we've got 2 molecular ion peaks, but this time they should be present in a 3-to-1 ratio. So if you measured the height of this one, you should find, if you stacked it on top of each other 3 times, it would be the same height. Okay? So this is indicating that we've got chlorine 35 and chlorine 37. The most abundant one is the lower mass one. If you remember, the average mass on the periodic table is 35.5, yeah, the weighted average mass, then that helps to remind you that's closer to 35 than it is to 37. So this is the one that there's 75% of, and this is the one that there's 25% of. Okay. So now you've got some questions for you to try. So I think you'll find A and B relatively straightforward, C a little bit hard, D pretty hard. I need to go to the loo though, so whilst you're doing that, I'll be back in 1 minute. If anyone else needs to go to the toilet or get a drink of water, please do. But I'm going to leave you on, Stella, so I don't forget. I'm going to leave the thing recording, because otherwise I'll just forget. Actually, no, I'll turn the recording thing off on here, but I'll leave Stella on so I don't forget to bring her back.